So this is a long problem. Let's just go ahead and get started. At the beginning of the compression process of an air standard Otto cycle, the properties are the pressure is 1 bar and the temperature at state 1 at the beginning of the compression process is 300 Kelvin. The maximum temperature of the cycle is 1950 Kelvin and the compression ratio is 10.2. Now there's a lot of questions. Let's just go through them, but I will not be able to solve this whole problem on one page. I'll have to go to multiple pages. So they ask, what is the heat addition per cycle, then the heat rejection per cycle, then the net work per cycle, then the thermal efficiency, mean effective pressure, and then do a full Exergy accounting for the whole cycle, and then devise and evaluate an exergetic efficiency for this cycle. Well, that's a lot. So basic process is to put in a diagram. You want to be able to sketch it. So we have a pressure. I'll put specific volume diagram. We start at low pressure, large specific volume. That would be state 1. And then we undergo a compression process. And that compression going down to state 2, V sub 2, is like 10.2. So 1 over 10.2. So V sub 2 is 1 over the compression ratio, 10.2 times V sub 1. I'll put V sub 1 there and put V out like that. Okay. So it's, you can try and draw it to scale. And the pressure goes up, temperature goes up, that's state 2. Now for the Otto cycle, we stay at constant volume and we add heat up to state 3, and that gives us our maximum temperature. And then we expand in our power stroke down to the same specific volume. So V4 and V1 are the same. And then constant volume heat rejection. Now you can also put it on a temperature entropy diagram. So we start at low temperature and low entropy, state 1. And then it's isentropic. Sometimes we'll put S equal to a constant, emphasizing on the PV diagram that the process 1 to 2 is isentropic compression, and the process from 3 to 4 is isentropic expansion. Well, isentropic is straight up on a TS diagram. So 1 to 2, it's just straight up. Then we go out at a pressure equal to a constant heat addition to state 3. Then straight down for isentropic expansion to 4, and then pressure is equal to a constant heat rejection from 4 to 1. Okay, so it's good to get the diagrams. Then we also want to construct a table. 2 tables, I think, help us. One is all about properties, and the other is all about the energy balance. Okay, so and also we can do an Exergy balance, because at the end they're interested in Exergy calculations. So really even more than 2 tables, but 2 at the basics. And you would just say, what are my states? And you'd say state 1, 2, 3, 4. And what are what's the pressure? You can work in bar, kilopascal. My preference is kilopascal, but your preference could be something else. Temperature, my preference is Kelvin. You could put degree C, whatever. You could put volume or specific volume in here if you wanted to. And it is air as our working fluid, so we always have the ideal gas equation ready to go. And so now we can start putting in property. Let's say 100 kilopascal and 300 Kelvin, and you could calculate that specific volume. I'm not certain I did that. I think I did. It's 0.86096 meter cubed per kilogram. All right, it's not that important, but you could calculate more properties. Okay, let's take a look. Where is that maximum temperature? Well, it's at state 3. So we jump down here. It's 1950. That's given in the problem statement. 1950 Kelvin for the maximum temperature. Okay, and do we know anything else? Well, you could do the compression ratio and you could get the V at 2. You just take that V and divide by 10.1 1, you would get 0.08441, and V sub 2 and V sub 3 are the same, so you could flush that out, 441, and then back to 0.86096. Okay, for what it's worth, we got those. Now, how do I calculate the, let's say, the temperature at 2 or the pressure at state 2? Well, it depends on your assumption, and you have to read the problem statement carefully. Did it say a cold air standard analysis? If it did, you would use constant specific heats evaluated at 300 Kelvin. But it didn't say cold air. All right, we look around in the problem statement. Did they say use C sub V equal to, or C sub P equal to, or K equal to? Nope, they didn't give us any particular values of C sub P, C sub V, or even K. Even if they just gave us K by itself, we could get C sub P and C sub V. So what do you want to do? We have to make a decision. Are we going to maybe do a cold air standard analysis? Maybe do a warm air standard analysis with some average appropriate C sub P, C sub V, and K? Or are we going to use the table? The table A22, the air table, and do it that way. That would be the most accurate, using or accounting for temperature dependent specific heats of the air. And say, okay, so, well, let's go ahead and use the air table. And so how would I solve for this compression process from 1 to 2? Well, we know that it's isentropic, S equal to a constant. And there's a particular column in the air table for what we call V sub R. I'm just going to get rid of this. I don't have enough room to put all these tables on one slide. And we can look up the V sub R as only a function of temperature. And at 300 Kelvin, the V sub R comes in at 621.2. 621.2. That's a data point in the table A22. Now, how do we use it? Well, we know that for an isentropic process, the ratio of specific volume at 2 divided by the specific volume at 1 is V sub R at 2 divided by V sub R at 1. And we look at this equation and we say, I know the ratio of specific volumes. That's basically 1 over the compression ratio. And I know V sub R at state 1, I can actually calculate V sub R at state 2. Well, V sub R at state 2 is just V sub R at state 1 divided by 10.2, the compression ratio for this problem. And it comes in at 60.902. Okay. More digits in there, but now that you know the V sub R at state 2, you can look up the temperature at state 2. Okay, so now you find T2 as a function of V sub R2 in our table. And when you do that, you'll come in with a temperature of 735.3. Interpolation. One of the things that I do not like about using the tables like this is a lot of interpolation. Very hard to have these numbers just line up on a line in the table. You're always interpolating. Okay, now that I know the temperature and the specific volume at state 2, I can calculate the pressure. Just go back to the ideal gas equation. PV at state 2 is equal to R T2. It's like I know T2, I got R as a constant, gas constant for air. I know V2, the only unknown is P2, so we go ahead and calculate the pressure. So it's 2500.1. All right, now they gave us the temperature at state 3. We know the specific volume at state 3, and so it's a very similar equation. P3, the unknown, we have V3 equal to RT3. You can calculate that pressure. at state 3, 6630.0 kilopascal. Again, how did that, well, you're given V3, R, and T3. Now calculate P3 in that equation. Okay, now that you have the temperature and the pressure at state 3, really the temperature allows you to calculate V sub R at state 3. So we'll come over here, we look up V sub R at 1950 Kelvin. That comes in at 3.022. We undergo isentropic expansion. So you multiply, just like this one was, you multiplied by 1 over the compression ratio. Here, because it's expansion, you multiply by the compression ratio. In this problem, it's 10.2. So that comes in at 30.824. Do the same thing, interpolate to get the temperature, knowing V sub R in the table. That temperature comes in at 933.8. And then go ahead and get the pressure. Very similar. I mean, it's like P4 V4 is equal to RT4, so you can calculate 311.3 kilopascal. That's a lot of work. Well, while we're doing that, if we're going to stay in the table, go ahead and get the U's out of the same table, which are in kilojoules per kilogram. Get the specific heat at constant volume. So it turns out to be 214.07. And then it's 540.30. And then 1630.60. And 702.90. Okay, now I've got to make some more room. I hate that, but I need to get rid of this. And I need to continue this table, because not only are we going to have an energy balance, but we're going to have Exergy balance equations. And so if we're going to do the Exergy calculations correctly, I'm going to need to get a little more information. So this is what I did, is you can calculate that S naught. What is that? That's in units of kilojoules per kilogram Kelvin. And you can calculate it as a function of temperature only, 1.70203, and then 2.62588, and likewise 3.76770 and 2.89001. Okay, now that I have the S naught, what I want to do is I want to say, well, what is my dead state for an Exergy calculation? And it's 300 Kelvin 1 bar, which is kind of nice because it matches. This is the same as state 1. So state 1 is equal to the dead state. I don't know if I'm writing that well, but the pressure at state 1 and the dead state temperature are the same. So it's just make that comparison. So what we can do is we can say, what is the change in S naught from the dead state S? Now, let me back up. If I wanted to, I'd say, what is S at state 1 minus S naught, the dead state? Well, that would be S1 naught minus S naught. How do you like that? These are that symbols, and then you would put the minus, the R, natural log, and I ran out of room. Oh, terrible. I'm going to move that over so I can see that equation. So it's equal to minus R times the natural log of P1 divided by P naught. Okay, so what I'm going to do is not just calculate the difference in the low pressure, like 1 atm, changes in entropy, but the full thing accounting for the change in pressure compared to the dead state pressure. And so this is S minus S naught for state 1. Well, that change in entropy is 0 because it's it's the same pressure and temperature. But for state 2, we can calculate that S minus S naught. It's extremely small. It's essentially 0 again, because from 1 to 2 it was isentropic. Okay. Now it's 0.862 and 0.862 for the last two states, state 3 and 4. All of that just so I'm ready to calculate the exergy. What do you mean exergy? Not the flow exergy, but the exergy of the air at each of these states. All right. Well, what was my equation? I got to erase some more up here. Isn't that terrible? Okay, just erase a bunch. And so we calculated the change in S, but you have the exergy is equal to U minus U naught plus P naught V minus V naught minus T naught S minus S naught. Okay, so we just calculated this S minus S naught. That's this column. We multiply it by T naught, the dead state temperature in Kelvin, 300 Kelvin. Subtract that from V minus V naught. Well, the V naught is this V at state 1, because that's the same as the dead state. So you subtract that, multiply by the dead state pressure in kilopascal, so the units work. It'll be 100 kilopascal. And then U minus U naught. Well, we have all the tools. We go ahead and make the calculation of the exergy at state 1. It's 0. The exergy at state 2 is 0 as well. No, it's not 0. It's 248.55. Okay. And then it's 1080.3. I'm going to round off. And then 230.2. What are the units on this? Kilojoules per kilogram. What were the units on the change in S? Kilojoules per kilogram Kelvin, kilojoules per kilogram Kelvin. And of course I ran out of room, but there you go. These numbers are going to be needed when we do the exergy balance. Okay, well, what I need to do is I need to go to another slide. There's no easy way to solve a long problem on one slide like this. So we'll go to another slide and we'll put together a table of energy transfers. So the table of energy transfers. All right. It's just bookkeeping to help you keep things straight. And so it's per the process. So we have the process from 1 to 2, from 2 to 3, from 3 to 4, and 4 back to 1. So those are this is a bad looking 2. Those are the processes. And then you can describe them. What was the process? Well, was adiabatic compression and reversible, hence isentropic compression. You can make some notes if you like. I don't have a lot of room here, but I like to do that. You know, it's just reminding me what's happening during these processes. And then I look at the energy balance. Well, the energy balance equation is what is my change in the specific internal energy, and what is my Q per unit mass and my work per unit mass. So Q in, work out, we'll keep that sign convention so that when we do the tabulation and sum all the Q's to get Q net and sum all the W's to get work net, everything will work out perfectly. So you can come in here and make 3 columns to help you. What is the change in U? Well, for process 2 to 1, I'm just going to write it out. It's U2 minus U1. And then for process 2 to 3, well, it would be U3 minus U2. Well, we have those data out of the previous table, don't we? So instead of just writing them symbolically, you can just make the calculation. This was 326.23, sorry. 326.23. And then it's 1090.30, then negative 927.70, and then negative 488.83. Now, some are positive, some are negative. Well, the change in internal energy was increasing or decreasing. And when you take the sum of all of these, what should it be? That whole column? It better be 0 or look for an error. Okay, then we do the same thing for the Q's. So these were units of kilojoules per kilogram. These are all units of kilojoules per kilogram. And then the W's in kilojoules per kilogram. All right, but we have to go slow. Some of these values are 0, so populate the table with the 0 values first. Well, it's adiabatic compression and adiabatic expansion. And then it's constant volume heat addition, constant volume heat rejection. So half of the Q's and half of the W's are 0. And then you say, well, what is the W over here? Well, you just look at the first law. If just kind of go back to this equation each time. And so for the process 1 to 2, Q is 0. So this is just negative 326.28. Almost too easy. Might as well come down and do the process 3 to 4. Well, it's going to be negative of a negative, so it's positive 927.70. And then likewise, you come over here to go back to the first law for the process 2 to 3. When the work is 0, well then Q 2 to 3 is equal to delta U, so it's 1090.30, and this is negative 488.83. Okay, so sum the Q's to get Q net, and when you get Q net, you find that it's 601.47. Sum the works to get work net. When you sum that column, 601.47, they match, they need to match. If they didn't match, look for an error. So this is good. I checked, I was like, okay, at least I haven't detected an error. I may have made an error somewhere, but at least I haven't detected it, and I'm still going good. Well, do this. Just go ahead and extend that table, and here, just instead of an energy transfer, think of exergy transfer. All right, well, what's going to be our exergy balance equation? Just like this was our energy balance equation, what is a good exergy balance equation? So you can have the change in the exergy, and I like to put a little extra x on that. The book doesn't, but I like to, so it's it's different than the energy, specific energy, like you learned in chapter 2 in Thermo 1. Okay, well, you can have the exergy transfer. I'm going to write it like this. EX transfer with the heat. That would be coming in if the heat was coming in. If the heat was negative, heat transfer is negative, then we'll be taking it out. Then we're going to have minus the exergy transfer with the work. If the work is positive out, then that's an out. So we keep a negative sign on this exergy balance equation. And the other term is we could have some exergy destruction during the process. Well, what's the cause of exergy destruction? Well, the cause of exergy destruction are irreversibilities. So this exergy destruction term you might think of as T naught times the sigma, let's say, entropy generation during each of these processes. Well, we're studying the Otto cycle. The Otto cycle is every process is reversible. Hence, guess what the exergy destruction is for each of these is 0. Okay. So what we do is we come over here and we construct just like we did for the energy balance. What is my change in the exergy? Well, let's just write it out. It would be the exergy at state 2 minus the exergy at state 1, and then the exergy at state 3 minus the exergy at state 2. Well, we already computed all these exergies just like we computed all the internal energies. And so we just go back to our table and we make the calculation. 248.55, then 831.73, then negative 850.08, and negative 230.20. All right. Now, if we sum that column, because the Exergy destructions are 0, what should we get? We should get 0. So there's no Exergy being destroyed. The changes in Exergy sum all up to 0. Now, you can take a look at some of these. It's positive here, positive here. It was positive over here, wasn't it? And positive over here. Negative over here, and negative over here. Well, it's negative over here, negative over there. But the magnitudes aren't exactly the same. Well, what's the difference? Well, it's not just, the Exergy is the useful amount of energy. And so when you're having, especially when you're having compression or expansion, the boundary work of pushing back the atmosphere has to be subtracted, or is subtracted in the Exergy calculations. Okay, so let's continue on. Well, we want to have a term here for what is my Exergy transfer with the heat transfer, and this is kilojoules per kilogram, just like this is kilojoules per kilogram. And then I'm going to just tuck it in, Exergy transfer with the work and kilojoules per kilogram. Well, if you have no heat transfer, can there be Exergy transfer with? No. So half of this table is 0. Why? Because it's adiabatic. There was no heat transfer. Likewise, constant pressure heat addition, constant pressure heat rejection. So good, we got 4 of the 8 values calculated. And then how do we calculate the, let's say, the Exergy transfer with the work for the process 1 to 2? Well, you go back to the Exergy balance equation. You say, well, there's only one term that's non-zero on the right-hand side. Hence, we calculate this to be negative 248.55. Do it for the heat transfer. Go back to the Exergy balance equation for the process 2 to 3, and we find that it's in 831.73. That's a positive in front of it. Then I'm a negative of a negative 850.05. Or is that 08? Sorry. And then over here, it's the negative 230.20. When we do the sum of the Exergy transfers with the heat coming in, we find 601.53. We do the sum of the Exergy transfers out with the work, 601.53, because there's no destruction. There's no accumulation in the cycle of Exergy. It's a cycle, and so these match. These are the same. If there would have been some destruction, well, then they don't match because there's destruction. But because there's none, there you go. Well, at this point, basically, you have all the questions answered. I have to go back a slide. I hate to do that. But you say to yourself, what is the heat addition per cycle? Well, that's only the heat that's coming in. It's around 1090. Where did we find that in this table? Well, it was around 1090. That's the only place that the heat is added in 2 to 3. Oops, I should have underlined it right here. Sorry. This is a heat rejection from 4 to 1. All right. What is a heat rejection? Well, it's 488. Did I type that wrong? No, 488.83. Good. That's the heat rejection. Answer to part B. What is the net work per cycle? Isn't that the net work per cycle? 601.47 kilojoules per kilogram. Now, what is the thermal efficiency? Well, you just take the thermal efficiency of the cycle. That's the work net, 601.47, and you divide by the heat that you had to pay for to bring in, 1090.3, and you get the thermal efficiencies right at 55.2%. Okay, go back and just check. Yeah, 55.2%. What is the mean effective pressure? Okay, well, what is the mean effective pressure? Well, if you multiply the mean effective pressure by the displacement volume, the specific volume that's being displaced, V displace, you'll get the W net. Okay, so to calculate the mean effective pressure, I just divide by displacement, clean this equation up a little bit. So I take my 601.47, that's kilojoules per kilogram, okay, and we divide by the specific volume. Well, this is for the displacement only. So you came in at state 1 and you went out at state 2. So it's this displacement volume is V sub 1 minus V sub 2. And did I make that calculation? Let me take a look if I did. Yeah, it's 0.77655 meter cubed per kilogram. Okay, and then the units, when you run it, the mean effective pressure comes right in at 774.5 kilopascal. They want it in bar, move it over by 2, so it's 7.745 bar. Go back and check. Did we get that right? Yeah, there we go. Okay, now the full Exergy accounting. Well, let's take a look at the answers here first. They have the Exergy in with the heat transfer. Okay, then the Exergy out with the heat. Just, it's very similar, just you're dropping the minus sign there because we know it's out. Okay, then the Exergy out net work for the cycle, 601.5, and then the Exergy destruction for the cycle. So if we come here, they're asking for this Exergy transfer in with the heat, Exergy transfer out. I know they got rid of the minus sign there. And then the Exergy net with the workout, 601. And the last part, devise and evaluate an exergetic efficiency for the cycle. Well, you come over here to this thermal efficiency, and it's what you wanted over what you had to pay for. And you just do the same thing. You come over here and you say, I'm not going to have a thermal efficiency, I'm going to have an exergetic efficiency. Now what do I want? I want a whole lot of the Exergy, net Exergy out. So this would be here EXW net, something like that. I know the numeric value of that, 601.53 kilojoules per kilogram. Okay, but what did I have to pay for? How much Exergy did I bring in? I only brought it in heat transfer, in that process from 2 to 3. EX, the Q in, is 831.73, and so we can get an exergetic efficiency of 72.3%. Now, I'll just say that these are conceptually interesting calculations, but on a simple problem like this, it's pretty rare that this is blown out and put on an exam. But hey, we have a homework problem, we've done it, we are taking what we learned in the previous chapter, chapter 7 with Exergy, bringing it forward into chapter 9 when we're studying gas power cycles, and we can still make these calculations. So with that, 72.3, and we are done with this problem.